Introduction. The purpose of this lab is to compare observed projectile motion to computationally predicted projectile motion, both accounting for and not accounting for drag. In the experiment, we used a crumbled up paper ball, this being our system, whose mass was recorded and was thrown in the air. The air, force of gravity, and anything else that could act upon the ball was our surroundings. A recording of this was taken and put into a tracker where the displacement of the paper ball from its maximum height to near the end of its downward trajectory was observed and recorded frame by frame over a course of 0.267 seconds. And all the ball had displacement and velocity in the x direction. These were disregarded in the study, which if you saw the pre-lab videos, they only focused on the y direction of the ball, so that is why the x direction in this study was omitted. We are only observing and considering motion, velocity, acceleration, and forces in the y direction of this experiment. Here is a photo of the ball in tracker, where as you can see, the position of it was plotted from the top of its trajectory to shortly before hitting the ground. Since we know that the trajectory of a projectile motion is a symmetrical parabola, this allows for us to visualize what the full parabola would look like, regardless of where the ball was originally released from the hand. Review of results. The observed position and predicted position without drag were very close. The observed position was seen falling faster than the predicted position without drag. Since drag would push up on the ball against the force of gravity, it should make the ball slow down and fall slower than the predicted position. Since this is not the case and how similar the observed and predicted position without drag are, drag can be assumed to be negligible in this experiment. Here we see the actual downward trajectory of the ball in blue, and then we have the predicted downward trajectory of the ball in red. As you can see, the actual trajectory fell faster, and due to this, we can assume that drag is negligible because adding any drag to it would cause the predicted position to fall slower and be further away from the actual position. Due to this, we assume that drag force is 0 and only have a non-drag force computational model, because having a drag force would make it less accurate in comparison to what occurred in actuality. So that being said, however, we still put drag force in our computational model. We just set the proportionality constant to 0. Physics ideas used. In this study, we used kinematic equations, Newton's second law, drag, and gravity. Here are the kinematic equations we use, the velocity update formula and the position update formula. We use these so the computational model could do iterations and constantly update what the current velocity of the ball and what the current position of the ball should particularly be. We use Newton's second law to prove that net force acting on the ball is its mass times its acceleration. We only use this to prove that acceleration equals F net divided by mass to put into the velocity update formula because it calls for acceleration. And this isn't a part of Newton's law, but we also know that F net is the force of gravity plus the force of drag. And in the y direction, which is the only direction we are worrying about, they act against each other. The force of drag equation is proportionality constant times the magnitude of velocity squared multiplied by negative v hat because it is in the opposite direction of velocity. And the last equation we have is the force of gravity, which equals mass times the gravitational constant times negative y hat because the force of gravity always pulls in the negative y direction. Here's the code for the computational model. The velocity in the x direction is set to 0, even though at the start of the observed time it did have x velocity because, as aforementioned, we're only worried about motion in the y direction. We set w as a constant that is equal to the force of gravity in the y direction, which is the total force of gravity. We made a vector that is going opposite of the velocity of the ball and is the magnitude of the drag force in the y direction, and we have it going in the positive y direction to be going opposite of the velocity of the ball. And we add a vector accounting for the force of gravity to the vector accounting for the force of drag, and that gives us our net force. Here's our output of the code. The assumptions we made in this study is that net force is constant, mass is constant, drag is negligible, acceleration is constant, and that the only forces that could be acting upon the ball in the y direction during the observed time are drag and gravity. The observed position and predicted position without drag were very close through the 0.267 observed seconds. The observed position was seen falling faster than the predicted position without drag. Since drag would push up on the paper in the y direction against its downward velocity and in turn the force of gravity, it would make the ball slow down and fall slower than the predicted position without drag. Since this is not the case and how similar the observed position and predicted position without drag are, drag can be assumed to be negligible in this experiment. As discussed earlier, our graph with drag and our graph without drag are the same because we found that drag is 0 because the falling of the ball in actuality fell quicker than the predicted position of the ball. Discussion/conclusion. Assuming that the recorded observed position of the paper ball is perfectly correct, the fact that the observed position was seen falling faster than the predicted position without drag implies that another force besides gravity and drag is acting on the ball in the y direction, making it fall faster than predicted with solely the force of gravity, computationally. We know that this is the case because drag force always acts on a system in the opposite direction of velocity. It would be impossible for drag force to make the ball fall faster than it would solely with gravity acting upon it because the force of gravity makes the ball's velocity in the y direction negative, and thus the y component of drag force would be in the positive direction. This would slow down the ball. Due to this, the result implies that there is another force whose y component is greater than that of the force of drag acting upon the ball in the negative y direction and making its velocity in the y direction greater than it would be with solely gravity acting upon it. But let's be for real. It's much more likely that drag force is very small and negligible, and the observed position falling faster than the predicted position was due to an error. Possible sources of error: human error in pinpointing the position of the ball in tracker during each frame, and coding error, but this is not likely due to the fact that the code seemed to run well otherwise. What does it mean? Here's the what does it mean question that you can review, but it was also in the lab instructions. Here's a graph of the computationally predicted y component of the velocity of the ball. So no, none of the models predict terminal velocity, as velocity is never constant and always changing. There's always a force acting upon the ball in the negative y direction, the magnitude of the force being the magnitude of the force of gravity minus the magnitude of the y component of the drag force. Since in our experiment drag was negligible, its magnitude was solely the magnitude of the force of gravity acting upon the ball. To find terminal velocity, the ball would need to experience a drag force on it with a magnitude that is equal to the force of gravity. To do this computationally would be easy, as all that would be needed is to set the drag force equal to the force of gravity. To design an experiment with terminal velocity, the system that is falling would have to be made much less aerodynamic, and or the medium the system is falling through would have to be a denser fluid than tropospheric air. Here's the what if question. Feel free free to review it. The initial speed of the object was prior to the observed frames, as the observed frames were solely from the apex of the ball's trajectory until shortly before it hit the ground. The object's initial speed was when it was leaving the hand that threw it. The ball's initial velocity was split up into an x and y component, and speed is the magnitude of velocity, and the y component of velocity is the only component of velocity that affects the amount of time it takes the ball to reach the ground. If the ball was thrown straight up with the same initial speed, it would take longer to reach the ground than it did in the original experiment. This is because all the speed would be in the positive y direction and not split up between the positive y and positive x directions. This can be seen by doing iterations with kinematic equations, the velocity update formula, and the position update formula. As with a greater initial velocity in the y direction, it would take longer for the force of gravity to slow down the object, and the object was displaced for longer than in the original experiment going up, and since the apex of its trajectory would be higher, it would displace for longer coming down as well. Thus, if the object were thrown straight up with the same initial velocity as in the experiment, it would take the object longer to reach the ground. Here's the glow script code. Thank you.